Hello there, and welcome to the Sleepy Science Channel. Tonight, we are drifting into the cosmic web, the vast hidden architecture that binds the universe together. Far beyond the stars we see, galaxies are not scattered at random. They gather along immense threads, stretch across luminous walls, and surround great dark voids so large they seem to challenge imagination itself. This is the universe on its grandest scale, a structure shaped by gravity, dark matter, ancient light, and tiny ripples left behind from the beginning of time. The cosmic web is where galaxies are born, where clusters grow, and where some of the universe's deepest mysteries are written into space itself. It is a map of everything becoming connected, from the faintest hydrogen clouds to the largest structures ever discovered. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Let your shoulders soften. Allow your breathing to slow. And as your mind begins to loosen its grip on the day, join me as we explore this vast cosmic web together. Let's begin. The universe is arranged like a vast web, not a random scattering of galaxies. When astronomers first mapped galaxies in 3 dimensions, the picture was not a smooth spread of lights. It looked organized, almost biological. Galaxies gathered into long chains, broad sheets, crowded knots, and enormous hollows. The pattern stretched farther than any single galaxy, farther than clusters, farther than anything people had imagined when they first pointed telescopes at the sky. This changed the way we understand space itself. The universe is not just filled with objects. It has architecture. Matter collects where gravity has slowly gathered it, leaving other regions thin and sparse. If you could fly outward beyond the Milky Way, beyond nearby galaxies, and beyond entire clusters, you would begin to see this immense design. It is the largest pattern known in nature. Every star, planet, and person belongs somewhere inside it. Galaxies gather along invisible threads longer than the imagination can hold. The bright galaxies we see through telescopes are only the lanterns marking something larger. They line up along vast strands that cross the universe like cosmic highways. These strands can run for distances so enormous that light itself needs hundreds of millions of years to travel from one end to the other. Yet they are not solid beams or glowing ropes. Much of their mass is hidden, made of dark matter and thin gas spread so widely that it barely shines at all. Astronomers find them by measuring galaxy positions, by watching how gravity bends light, and by searching for faint traces of gas between worlds. The result is astonishing. Space has roots. Galaxies are not sprinkled randomly through the dark. They often gather where the universe has laid down its deepest lines of gravity. Dark matter forms the hidden skeleton of the cosmic web. Most of the matter shaping this enormous structure cannot be seen directly. It does not glow, absorb light, or reflect starlight into our telescopes. Yet its gravity is unmistakable. Long before ordinary atoms could settle into stars and galaxies, dark matter began gathering into clumps and strands. Those invisible concentrations became the framework that later guided gas, galaxies, and clusters into place. Without it, the universe would look very different. There may not have been enough gravitational pull to build the rich structure we observe today. Scientists can trace this unseen framework by studying how galaxies move and how distant light is distorted as it passes through massive regions. It is strange to think that the visible universe is only the decoration on something deeper. The grandest architecture in existence may be built mostly from what we cannot yet identify. The biggest known structures are not galaxies, but galaxy filaments. A galaxy already feels impossible to grasp. The Milky Way alone contains hundreds of billions of stars, along with dust, gas, planets, black holes, and hidden matter. Yet galaxies are not the largest things in space. They are small pieces inside even greater structures. Filaments can connect clusters and superclusters across distances that dwarf individual galaxies completely. Some are so immense that they make the Milky Way seem like a single grain within a continent. These structures are not objects with sharp edges. They are vast regions where matter is denser than average, stretched into long forms by gravity and cosmic expansion. Their discovery changed astronomy from the study of isolated islands into the study of a connected landscape. The universe has mountains, valleys, threads, and crossings. Galaxies are its cities, but filaments are the roads between them. Empty cosmic voids can be larger than hundreds of millions of suns. Between the great strands of matter lie regions so vast and sparse that they almost feel like absences carved into space. These voids are not completely empty. They may contain faint galaxies, thin gas, and dark matter, but compared with the crowded filaments around them, they are astonishingly bare. Some stretch across hundreds of millions of light years. Imagine crossing such a region and finding almost no great galaxy clusters along the way. For astronomers, voids are not just gaps, they are clues. Their size, shape, and growth reveal how matter has moved over cosmic time. As gravity pulls material toward denser regions, voids become emptier and larger. They are the negative spaces of the universe's design. Without them, the web would not have its shape. Emptiness itself becomes part of the story. Our Milky Way lives inside one strand of this vast web. Our galaxy may feel like the center of everything because it is our home, but on the largest maps, it is part of a far greater arrangement. The Milky Way sits within a local region of galaxies that connects to larger flows and denser structures beyond. Nearby galaxies, including Andromeda, are moving under the influence of gravity that reaches far outside our small neighborhood. On cosmic scales, our home is not isolated. It is embedded in a network of matter that links galaxy groups, clusters, and superclusters together. This gives our location a new meaning. Earth is not only orbiting the Sun. The Sun is not only circling the Milky Way. The Milky Way itself is moving through a grand strand of cosmic structure. Even at rest in your chair, you are traveling within the web. The cosmic web began as tiny ripples in the newborn universe. In its earliest visible state, the universe was almost smooth. Matter and radiation filled space in a hot, dense glow, but it was not perfectly even. There were tiny differences from place to place, little variations in density that later became unbelievably important. Where matter was slightly denser, gravity had a little more to work with. Those regions pulled in more material, which made them denser still. Over billions of years, small beginnings grew into enormous consequences. The faint ripples recorded in ancient light became the seeds of galaxies, clusters, filaments, and voids. This is one of the most beautiful ideas in cosmology. The largest structures now known were once almost invisible. A difference too small for the eye to imagine eventually became the architecture of the universe. Vastness grew from almost nothing. Gravity turned faint imperfections into the universe's grandest architecture. Gravity is not fast in the dramatic sense. It does not build the cosmos with explosions or sudden gestures. It works patiently, amplifying whatever small unevenness already exists. A slightly denser region attracts more matter. As more matter gathers, its pull becomes stronger. Nearby material begins drifting inward, while less dense regions lose matter and become voids. This feedback, repeated across billions of years, shaped the web we see today. The process is simple in principle, yet the result is breathtakingly complex. It made galaxy clusters at the busiest intersections, filaments between them, sheets around voids, and great hollows where matter thinned away. The universe did not need a blueprint in the ordinary sense. It needed physical laws and time. From tiny differences, gravity composed a structure larger than any object we can point to. Most galaxies are not alone, but threaded into cosmic highways. A galaxy drifting entirely by itself is not the usual story. Many galaxies belong to groups, clusters, chains, or wider structures that guide their surroundings. These great lanes of matter can influence how galaxies grow. Gas may flow along them. Smaller galaxies may travel through them. Clusters may build themselves at the places where several lanes meet. This makes the cosmic web more than a background pattern. It is part of galaxy life. A galaxy's neighborhood can affect its shape, its star formation, and the kinds of encounters it experiences. Some live in crowded knots where interactions are common. Others sit near the edges of voids with fewer neighbors and a slower pace of change. The web gives every galaxy an address. It tells us that location matters, even when the distances involved are almost impossible to picture. The cosmic web may hold missing matter scientists once could not find. For years, astronomers faced a strange accounting problem. Measurements of the early universe showed how much ordinary matter should exist, meaning matter made of atoms. Yet when scientists counted stars, galaxies, and hot gas in clusters, a large share seemed missing. The answer may lie in the thin spaces between galaxies. Much of this ordinary matter appears to be spread through the web as extremely diffuse gas. It is not dark matter. It is normal material made from particles like those in planets and people, but it is so thin and hot that it is very hard to detect. Astronomers search for it by studying distant quasars, X-rays, radio bursts, and subtle absorption signatures. The idea is captivating. Métis was not gone. It may have been hiding in the great connecting tissue of the universe all along. Galaxy clusters sit where the web's great threads meet. At the busiest crossings of the cosmic web, gravity gathers galaxies by the hundreds or even thousands. These places are not simply crowded neighborhoods. They are some of the most massive structures held together in the universe. Between their galaxies lies a vast atmosphere of superheated gas, glowing in X-rays, along with enormous amounts of unseen dark matter. A single cluster can bend light, trap galaxies, and reshape anything that falls toward it. Over time, smaller groups arrive along surrounding filaments and merge into the growing swarm. The result is a cosmic crossroads, where motion has been, flowing for billions of years. To imagine one is to picture an entire city of galaxies, each filled with stars, all moving through a shared gravitational sea. These intersections reveal the web at its most powerful. Cosmic filaments can stretch for hundreds of millions of light years. A single strand in the cosmic web can be so long that human scale disappears completely. Light from one end may need longer than complex life has existed on Earth to reach the other. Along that stretch, galaxies gather in chains, clusters mark denser knots, and faint gas fills the spaces between them. These structures are not drawn across space like neat lines. They twist, branch, thicken, and fade, shaped by the pull of surrounding matter. Their scale is one reason the cosmic web feels so astonishing. A galaxy is already a vast system, yet a filament can contain countless galaxies arranged along a path larger than most minds can comfortably hold. When astronomers map them, they are seeing not objects in the usual sense, but the shape of gravity, written across deep time. The web contains gas so thin, it is almost invisible. Much of the space between galaxies is not empty darkness. It holds atoms spread across such enormous volumes that the material can be thinner than the best vacuum humans can make on Earth. This gas is difficult to detect because there is so little of it in any one place. It may not glow brightly enough for ordinary images, yet it matters deeply. It can feed galaxies, record ancient chemical changes, and reveal how matter moves through the universe. Some of it is cold enough to leave delicate signatures in passing light. Some is heated by shocks, falling galaxies and growing clusters, until it becomes a faint, almost ghostly plasma. This hidden material turns the cosmic web from a simple pattern of galaxies into something more alive with process, motion, and history. Some filaments are detected by the shadows they cast on ancient light. Not every discovery in astronomy comes from seeing something shine. Sometimes the clue is what a structure does to light passing behind it. Ancient radiation from the young universe fills the sky in every direction. When that faint background glow passes through hot gas in cosmic filaments, it can be subtly changed. The effect is tiny, but with careful measurements across many regions, astronomers can tease out the presence of matter that would otherwise remain hidden. This is a beautiful kind of cosmic detective work. The filament itself may be too dim to photograph directly, but it leaves a fingerprint on older light. It is like finding a transparent thread because it slightly warms or dims the glow behind it. The universe reveals itself not only by brightness, but by interference, distortion, and trace. The cosmic microwave background carries the web's earliest fingerprints. Long before galaxies existed, the universe released a glow that still surrounds us today. This ancient radiation is almost perfectly even, but not completely. Across it are tiny temperature differences, faint variations that mark where matter was slightly denser or thinner in the early cosmos. Those minute differences became the starting map for everything that followed. Over billions of years, gravity deepened them into the structures we now call clusters, filaments, walls, and voids. When scientists study this old light, they are not just looking backward. They are reading the opening conditions of the cosmic story. The web we observe today is like a vast tree, and that background glow shows the first seeds in the soil. It is astonishing that the largest patterns in existence can be traced to such delicate markings. Dark matter clumped first, then ordinary matter followed its pull. In the early universe, ordinary matter was tightly linked with radiation, which made it harder for atoms to collapse into structure right away. Dark matter behaved differently. Since it did not interact with light in the same way, it could begin gathering under gravity sooner. It formed invisible wells and pathways before stars or galaxies had fully appeared. Later, ordinary matter fell into those gravitational landscapes. Gas collected, cooled, and eventually formed the first galaxies within a framework already prepared by dark matter. This changes the story of cosmic construction. The visible universe did not create its own stage from nothing. It settled into an unseen scaffolding that had been taking shape in the background. Every galaxy, including our own, may owe its birthplace to dark matter structures that formed before starlight became common. Voids are not truly empty, but they are astonishingly lonely. Look between the grand filaments, and you find immense regions where galaxies are rare. These spaces can stretch so far that an observer living in their middle might see a far emptier night sky than we do. Yet they are not perfect vacuums. They can contain small galaxies, drifting gas, and dark matter spread thinly through the darkness. Their loneliness makes them scientifically precious. In crowded regions, galaxies collide, strip gas, and transform one another. In voids, evolution may unfold more slowly and with fewer interruptions. A small galaxy there can become a record of what happens when cosmic life grows in relative isolation. These hollows also help shape the web by pushing contrast into view. The strands look striking because the spaces between them are so vast, dim, and sparsely populated. The largest voids contain far fewer galaxies than expected. Some cosmic emptiness is so extreme that it surprised astronomers when large maps first revealed it. In regions where simple intuition might expect many galaxies, only a scattered few appear. These enormous hollows can span distances that make even superclusters seem modest. Their existence shows that the universe has not spread matter evenly on every scale we can see. Instead, gravity has slowly drained material away from underdense regions and gathered it into surrounding boundaries. The rare galaxies inside these voids are especially interesting because they live far from the usual influences of dense environments. They may be smaller, bluer, or still forming stars in ways that differ from cluster galaxies. A void is therefore not just a blank on the map. It is a cosmic laboratory where scarcity itself becomes the experiment. Galaxies flow slowly from voids toward denser cosmic walls. The cosmic web is not frozen in place. Matter moves through it, pulled by gravity from less crowded regions into denser ones. Over immense spans of time, galaxies and gas tend to drift away from the interiors of voids and toward the sheets and filaments that surround them. This motion is far too slow for human senses, but across billions of years it reshapes the universe's large-scale pattern. The result is a kind of cosmic migration. Voids become emptier, walls become richer, and filaments grow more defined. A galaxy caught in this flow may not notice anything dramatic from 1 million years to the next, but its path is part of a grand movement. Space is expanding overall, yet gravity still organizes local matter into streams, borders, and gathering places. Cosmic walls are broad sheets where galaxies gather like frost. Before matter narrows into long filaments or condenses into clusters, it can spread across immense sheet-like regions. These walls are thinner in one direction and vast in the others, forming broad surfaces in the cosmic web. Galaxies collect within them in patterns that look very different from isolated groups. A wall may surround the edge of a void, marking the boundary where material has gathered after being pulled away from emptier regions. From our perspective inside the universe, these sheets can be difficult to recognize at first. They reveal themselves only when many galaxy distances are mapped together. Then the pattern appears, wide, pale, and enormous. They show that the cosmic web is not made only of strings and knots. It also has surfaces, membranes, and boundaries built from galaxies and gravity. Filaments act like feeding lanes for growing galaxy clusters. A cluster does not grow by waiting passively in space. It is supplied by the structure around it. Long strands guide gas, dark matter, and smaller galaxy groups inward, channeling material toward the densest knots. Over time, these inflows help clusters become heavier, hotter, and more complex. The process can be violent when groups fall in at high speed, stirring gas and triggering shockwaves. It can also be slow and steady, adding mass layer by layer across cosmic history. This gives filaments a role that feels almost like circulation. They are not just shapes on a map. They deliver matter to the places where gravity is strongest. Without them, clusters would be less connected to their surroundings. With them, a cluster becomes the swollen meeting point of many long cosmic roads. Some galaxies ride filaments into clusters like leaves on rivers. A galaxy entering a dense cluster often arrives along a larger route rather than from a random direction. It may travel with companions, drawn by gravity through a filament that has been guiding matter for billions of years. As it approaches the cluster, its environment changes. The surrounding gas becomes hotter. Encounters grow more frequent. Pressure can strip away the galaxy's own gas, making future star formation harder. In this way, the journey along a filament can end in transformation. A bright spiral may gradually lose the fuel needed for young stars. A small group may be torn apart and absorbed into the larger swarm. The image is powerful because it gives galaxies a sense of travel and fate. They drift through vast channels, then enter the crowded heart of the web. The web's shape depends on both dark matter and dark energy. Two invisible ingredients help decide the universe's grandest pattern, but they play very different roles. Dark matter gathers. Its gravity pulls material inward, building the hidden framework where galaxies collect. Dark energy does the opposite in a cosmic sense. It drives the accelerated expansion of space, making the largest separations grow faster with time. The web exists between these influences. Gravity tries to deepen structure, while expansion stretches the stage on which structure forms. By measuring how the web has changed across cosmic history, scientists can study this balance. A slightly different amount of dark matter would alter the density of strands and clusters. A different dark energy behavior would change how quickly growth slows down. The web is therefore not only scenery. It is evidence for the universe's deepest competition. Dark energy may be stretching the web apart over time. On the largest scales, space itself is expanding faster than it once did. This acceleration does not tear galaxies apart, because local gravity keeps them bound. It does not pull apart solar systems or planets. But across the huge distances between galaxy clusters and superclusters, it changes the future of the cosmic web. Regions that are not gravitationally bound can drift farther apart at increasing speeds. Over immense time, distant filaments and clusters may become harder to reach and impossible to observe as their light grows weaker and more stretched. This gives the web a future as well as a past. It is not merely growing richer forever. Some connections may slowly fall beyond one another's horizons. The largest architecture we can map today may one day become a set of isolated islands. The universe's expansion slowly widens the spaces between filaments. While gravity gathers matter into strands and clusters, cosmic expansion stretches the distances between the largest structures. This does not mean every object is simply flying outward through empty space. The space between distant regions grows, carrying unbound structures farther from one another. Over time, this helps voids become more dominant in volume. The web's dense regions remain important, but the great spaces between them occupy more and more of the cosmic map. This creates an extraordinary contrast. Matter becomes more concentrated in certain places, while the universe as a whole becomes more spread out. The process is slow beyond ordinary imagination, but its consequences are enormous. The web is not a static net. It is being drawn across an expanding cosmos, with its open spaces widening as gravity continues its local work. The web helps reveal where invisible mass is hiding. Astronomers cannot explain the motions of galaxies and clusters by counting visible stars alone. There must be more mass present, shaping the paths of galaxies and deepening gravitational wells. The cosmic web offers a way to locate this hidden influence. If galaxies gather along certain routes, if clusters bend light more strongly than visible matter allows, and if large-scale patterns grow in specific ways, then invisible mass must be part of the design. By comparing maps of galaxies with maps of gravitational effects, scientists can infer where the unseen material lies. This is one of the great achievements of modern cosmology. It turns absence into evidence. The web becomes a shadow map of mass, showing that the universe is shaped not only by what shines, but by what quietly pulls. Gravitational lensing can map dark matter without seeing it directly. Mass bends the path of light. That single fact gives astronomers one of their most powerful tools. When light from distant galaxies passes through a massive foreground region, its image can be stretched, shifted, or subtly distorted. By measuring those distortions across many galaxies, scientists can reconstruct where the mass must be. The remarkable part is that the method does not care whether the mass is bright or dark. Stars, gas, and dark matter all bend light through gravity. This allows astronomers to create maps of invisible structure across the sky. In some regions, these maps reveal dark matter spread along filaments and gathered around clusters, even where ordinary matter is faint. It is like studying a glass sculpture by watching how it warps a background pattern. The hidden shape becomes visible through its effect. Euclid is building a three-dimensional map of the cosmic web. A new generation of space observatories is designed to measure the universe not just as a picture, but as a vast structure with depth. Euclid observes huge numbers of galaxies across cosmic time, measuring their shapes and distances to study how matter is arranged. Its mission is especially important because the web's history can reveal how dark matter and dark energy have influenced cosmic growth. By examining weak gravitational lensing and galaxy clustering, Euclid can trace the scaffolding of the universe on enormous scales. This is not only map-making, it is a test of the laws that govern expansion, gravity, and structure. Each galaxy becomes a point in a greater pattern. With enough points, the web emerges in 3 dimensions, reaching across billions of years like a fossil record of cosmic evolution. Vera Rubin Observatory will help trace billions of web galaxies. From its mountaintop view, this observatory is designed to scan the southern sky again and again with extraordinary depth. Over years, it will build a changing record of the universe, capturing countless galaxies, supernova, asteroids, and other moving or varying objects. For the cosmic web, its wide survey will be especially valuable. Billions of galaxies can serve as markers of large-scale structure, revealing where matter gathers and how patterns stretch across the sky. Repeated observations will also improve measurements of galaxy shapes, which helps scientists study weak lensing and hidden mass. The result will be one of the richest cosmic maps ever made from Earth. It will not show the web as a simple glowing net. It will reveal it through statistics, motion, depth, and patient accumulation of light. The Sloan Digital Sky Survey revealed the web in breathtaking detail. One of the great turning points in modern astronomy came from measuring not just where galaxies appear on the sky, but how far away they are. This survey collected positions and distances for enormous numbers of galaxies, turning flat sky patterns into 3-dimensional structure. The result was a revelation. Long chains, broad walls, dense clusters, and deep voids appeared across the maps with stunning clarity. For many people, these images made the cosmic web feel real for the first time. It was no longer only a theoretical prediction from simulations and equations. It was visible in the distribution of galaxies themselves. The survey also allowed scientists to compare observations with cosmological models in precise ways. It transformed galaxies into data points, then transformed those data points into a portrait of the universe's architecture. Early galaxy surveys first showed that space had enormous structure. For much of modern astronomy, galaxies looked like scattered points across the sky. The missing ingredient was distance. Once astronomers began measuring how far large numbers of galaxies were, a hidden pattern started to emerge. Some regions were crowded far beyond chance, while others opened into vast, sparse spaces. The first 3-dimensional maps were rough compared with today's surveys, but they were revolutionary. They showed that the universe was not arranged like a random snowstorm of galaxies. It had depth, texture, and organization on scales that seemed almost unreal. Every new redshift measurement added another point to the map, and slowly the shape of cosmic structure appeared. It was like watching a continent rise out of fog. Those early surveys changed the question from "where are the galaxies?" to "why are they arranged this way?" The CF, a Great Wall, shocked astronomers with its impossible seeming scale. In the 1980s, a galaxy survey revealed a structure so large that it startled the scientific world. It appeared as a broad sheet of galaxies stretching across hundreds of millions of light years. At the time, many expected the universe to look fairly smooth on such scales. Instead, here was a wall of galaxies, enormous enough to make older expectations feel too small. It was not a solid barrier, but a vast arrangement of galaxies gathered into a sheep-like pattern. Its discovery showed that cosmic architecture could be grander and stranger than anyone had comfortably imagined. The name sounded almost mythical, but the evidence came from careful measurements of galaxy distances. Suddenly, the universe had landmarks on a scale beyond clusters. Space itself seemed to have geography, and the map was only beginning to be drawn. The Sloan Great Wall is among the universe's largest known patterns. Later surveys reached deeper and wider, and they uncovered structures even more immense. One of the most famous is a huge arrangement of galaxy-rich regions found in data from the Sloan Digital Sky Survey. It stretches across a staggering portion of space, linking concentrations of galaxies into a pattern far larger than any individual cluster. What makes it fascinating is not only its size, but what it reveals about cosmic mapping. At first, a structure like this can seem like one single object. Look closer, and it becomes a connected pattern of dense regions, shaped by the same processes that built the web. It raises a beautiful question. When does a pattern become a thing? In the cosmic web, boundaries are not always clean. The universe gives us forms that are real, but not simple. The Hercules Corona Borealis Great Wall remains controversial and enormous. Some claimed cosmic structures are so large that scientists debate whether they are truly single features at all. One famous candidate was identified through the distribution of gamma-ray bursts, which are brilliant flashes linked to extreme stellar deaths and other violent events. The pattern appeared across an immense region of the sky, far larger than most known structures. If interpreted as a single cosmic feature, its scale would be extraordinary. Yet the evidence is more uncertain than for galaxy surveys, because gamma-ray bursts are rare and difficult to use as clean tracers of structure. That uncertainty is part of the fascination. Cosmology is not only a catalogue of settled answers, it is also a field where enormous claims must survive careful testing. This possible wall sits at the edge between discovery and caution. Some enormous quasar groups may challenge how smooth the universe should be. Quasars are intensely bright centers of distant galaxies, powered by material falling towards supermassive black holes. Because they can be seen across vast distances, they offer a way to trace structure in the early universe. Some surveys have found very large quasar groupings that seem to extend across astonishing scales. These discoveries matter because cosmology assumes that, when viewed at a large enough scale, the universe becomes roughly uniform. Huge quasar associations test that idea. Are they genuine connected structures, or are they chance alignments in sparse data? The answer is not always obvious. Even when debated, they force scientists to sharpen their tools and definitions. A few bright points in the deep universe can challenge our sense of scale and remind us that the web may still hold surprises. The cosmic web is smoother on larger and larger scales. Up close, the universe is wildly uneven. Stars clump into galaxies, galaxies gather into groups, and groups collect along filaments and walls. But when astronomers zoom out far enough, those dramatic differences begin to average out. The cosmic web does not vanish, but its pattern becomes part of a larger statistical smoothness. This is crucial for modern cosmology. It means the universe can have enormous structures and still obey broad rules of uniformity at the greatest scales. Think of looking at a woven cloth. Close up, individual threads dominate your view. From farther away, the fabric looks even. The same idea helps scientists connect detailed galaxy maps with theories about the universe as a whole. Structure and smoothness are not enemies. They are different views of the same cosmic fabric. Cosmologists test the web to check the standard model of the universe. The great map of galaxies is more than beautiful. It is a stress test for our best cosmic theory. The standard model of cosmology combines ordinary matter, dark energy, expansion, and gravity into one working picture. From these ingredients, scientists predict how structure should grow over time. Then they compare those predictions with the web we actually observe. Are clusters abundant enough? Are voids the right size? Do galaxies gather with the expected strength at different distances? Each answer either supports the model or hints at something missing. This is why surveys matter so much. A pattern of galaxies spread across billions of light years becomes evidence about the contents and laws of the universe. The web is not only something to admire, it is something that can judge our deepest ideas. Simulations can grow virtual webs from the universe's earliest conditions. One of the most astonishing achievements in cosmology is that scientists can begin with a nearly smooth, early universe inside a computer and watch structure emerge. The simulation starts with tiny density variations, then lets gravity act across cosmic time. Dark matter gathers first into clumps and strands. Gas follows, heats, cools, and sometimes forms galaxies. Over simulated billions of years, a recognizable web appears. It is not drawn by hand. It grows from equations. That is what makes these experiments so powerful. They allow scientists to change ingredients and see what kind of universe results. Add different dark matter behavior, adjust expansion, or change the strength of feedback from galaxies, and the pattern responds. A virtual cosmos becomes a laboratory where the real cosmos can be tested. The Millennium simulation turned cosmic structure into a digital universe. When this landmark simulation was released, it gave scientists a dramatic way to explore how dark matter might organize space. It followed billions of particles under gravity, creating a vast synthetic universe where clusters, filaments, and voids developed from early conditions. The scale was breathtaking for its time. Researchers could track how structures formed, merged, and arranged themselves across cosmic history. The output looked strikingly web-like, with dense knots linked by long strands and separated by enormous hollow regions. It helped show that the cosmic web was not just an observational curiosity. It was a natural consequence of gravitational growth in a universe dominated by dark matter. For many people, the images became iconic. They looked less like ordinary charts and more like the nervous system of the cosmos. Illustris TNG follows galaxies forming inside a web of dark matter. More recent simulations go beyond gravity alone. They try to model the complicated lives of galaxies inside the web. Gas cools into stars. Black holes release energy. Exploding stars push material outward. Magnetic fields and chemical enrichment change how galaxies evolve. Illustris TNG is one of the major efforts to bring these processes together in a digital universe. Its value is not only that it creates beautiful cosmic structure, it shows how galaxies and their environments influence one another. A galaxy inside a filament may receive gas differently from one inside a crowded cluster or near a void. Feedback from galaxies can also heat and reshape surrounding gas. The web becomes more than dark matter scaffolding. It becomes the setting for galaxy formation, where environment and internal physics meet across billions of years. Cosmic simulations look strangely like real galaxy surveys. There is a powerful moment when a simulated universe is placed beside an observed galaxy map, and the patterns echo each other. The details are not identical, because no simulation is trying to reproduce the exact positions of every real galaxy. Yet the overall forms are familiar. Knots appear where clusters gather. Strands connect dense regions. Sparse voids open between them. This similarity is one reason cosmologists trust the broad picture of structure formation. The same basic ingredients that explain early light can also produce a modern web resembling the one telescopes reveal. It is a rare kind of scientific satisfaction. A universe built from mathematics begins to look like the universe outside. The resemblance does not end every mystery, but it shows that our deepest models are touching something real. The web's pattern comes from gravity, amplifying tiny beginnings. A slight density advantage in the young universe was all gravity needed. A region with a little more matter pulled a little harder. Because it pulled harder, it gathered more matter. Because it gathered more matter, it pulled harder still. This simple loop unfolded for billions of years, turning small differences into giant structures. The result was not uniform collapse everywhere. Matter collected into different shapes depending on the surrounding gravitational landscape. Some areas became knots. Some stretched into strands. Others emptied into voids. The wonder lies in the contrast between cause and outcome. The initial differences were incredibly subtle, yet their descendants are the largest recognizable patterns in existence. Gravity is often imagined as a force that makes objects fall. On cosmic scales, it is also the sculptor of form. Quantum fluctuations may have seeded today's largest cosmic structures. The story may begin at a scale far smaller than atoms. In quantum physics, empty space is not perfectly still. It can contain tiny fluctuations, brief variations in energy and fields. In the early universe, these minute irregularities may have been stretched to cosmic size during an incredibly rapid expansion. Once enlarged, they became differences in density across space. Later, gravity acted on them and built the web. This idea is astonishing because it links the smallest known physical behavior to the largest structures ever mapped. A faint quantum tremor may have become a chain of galaxies. A microscopic variation may have helped decide where future clusters would form. It makes the cosmic web feel like a bridge between two extremes. The universe's grand architecture may have roots in the restless behavior of reality itself. Inflation stretched microscopic ripples into galaxy-building cosmic patterns. In one leading picture of the early universe, space expanded at a tremendous rate during a tiny fraction of a second. This event would have taken variations that were once unimaginably small and enlarged them across vast distances. Afterward, those stretched ripples remained as slight differences in density. They were not galaxies yet. They were potential. As the universe cooled and evolved, those patterns guided where matter would later gather. This helps explain why the cosmic web has structure without needing some pre-existing cosmic design. Inflation took tiny variations and made them cosmologically important. Gravity then spent billions of years developing them into visible architecture. It is a story of scale transformation. What began in a realm beyond ordinary intuition became the framework for galaxies, clusters, and the great open spaces between them. Every filament carries a memory of the early universe. A strand of galaxies is not only a modern structure, it is a historical record. Its position, thickness, and connection to nearby clusters reflect conditions that existed long before stars were common. The web did not appear randomly at late times. It grew from an early pattern that was already present in subtle form. That means today's filaments still preserve information about ancient density variations, dark matter behavior, expansion history, and gravitational growth. When astronomers measure them, they are reading a fossil written in matter rather than stone. The idea gives cosmic structure a deep emotional weight. A filament may contain young stars and active galaxies, yet its outline remembers a time when the universe was hot, bright, and nearly featureless. The present still carries the imprint of the beginning. The web is still evolving, even as you listen. Cosmic change is usually too slow for us to notice, but it never stops. Galaxies continue to move through their environments. Clusters keep gathering material. Voids keep expanding in relative emptiness. Gas flows, heats, cools, and shifts between regions. The web we map today is only one frame in an immense cosmic film. If we could watch billions of years pass in seconds, we would see knots grow denser, strands stretch and feed them, and sparse regions become more pronounced. At the same time, accelerated expansion changes what can remain connected in the far future. This makes the web feel less like a fixed pattern and more like a living history of motion. The universe is not finished arranging itself. Its largest structure is still becoming what it will be. Galaxy clusters grow by swallowing smaller groups along cosmic filaments. A massive cluster is built through accumulation. Smaller galaxy groups approach along surrounding strands, drawn toward the deeper gravitational well at the cluster's center. As they fall in, their galaxies may be absorbed into the larger population, while their gas is heated and stirred into the cluster atmosphere. The process can leave traces, such as elongated shapes, disturbed gas, and streams of galaxies that still reveal the direction of arrival. This is how a cluster becomes more than a collection of galaxies. It becomes a record of many mergers over time. Each infilling group adds mass, energy, and history. The busiest nodes of the web are therefore not born complete. They are assembled through repeated arrivals, like great cosmic cities growing as smaller towns are drawn into their expanding reach. Superclusters are not always bound together by gravity forever. The word can sound more permanent than the reality. A supercluster is a very large region containing many galaxy groups and clusters, often arranged along parts of the cosmic web. Yet not every structure called a supercluster will remain together indefinitely. Some are associations seen across enormous distances, where expansion may eventually separate many of their parts. Gravity binds galaxies inside clusters strongly, but the larger supercluster region can be more loosely connected. This distinction matters because the universe is expanding, and dark energy affects the fate of the widest structures. A supercluster may be real as a present-day pattern without being a single lasting object. It is like a temporary province in cosmic geography, grand, meaningful, and measurable, but not always destined to stay united across the future. Our local supercluster is called Laniakea, meaning immense heaven. Astronomers identified this vast home region by studying galaxy motions rather than simply drawing borders around visible concentrations. Galaxies across our surrounding cosmos appear to flow along gravitational pathways toward a column basin of attraction. That flow helped define Laniakea, a name with a beautiful meaning drawn from Hawaiian language. It gives our cosmic address a sense of place, larger than the Milky Way, larger than the local group, and larger than familiar nearby clusters. The name is poetic, but the method is scientific. It is based on motion through the web, on the way galaxies respond to surrounding mass. This makes Laniakea feel like a watershed in space. Just as rainfall on Earth can drain toward a shared basin, galaxies can move within a gravitational landscape that reveals where they belong. Laniakea contains the Milky Way, Andromeda, and thousands more galaxies. Our immediate galactic neighborhood is only a small part of a much larger cosmic region. The Milky Way and Andromeda dominate the local group, but beyond them lie many groups, clusters, and galaxy flows that form part of the same immense structure. Laniakea spans a region containing thousands of galaxies, each with its own stars, planets, gas, and dark matter halo. Yet from the perspective of the cosmic web, they are all connected through large-scale motion. This changes the way our address can be spoken. We live on Earth, around the Sun, inside the Milky Way, within the local group, in the vast region called Laniakea. Each step outward reveals that home is layered. The more we map the universe, the more we discover that belonging can exist on astonishing scales. The Great Attractor pulls nearby galaxies through the cosmic web. Beyond the Milky Way, far past the familiar stars, there is a region of mass that has been tugging on our cosmic neighborhood for billions of years. Astronomers noticed it because nearby galaxies were not moving exactly as expected from expansion alone. Something massive was influencing their paths. The difficulty was that this direction lies partly behind the Milky Way's dusty plain, where our own galaxy blocks much of the view. That made the mystery feel almost hidden on purpose. Later studies showed that the pull is connected to dense structures and galaxy clusters beyond our local region. It is not a single monster object, but part of a larger gravitational landscape. The fascination lies in the motion itself. Whole galaxies, including ours, are being guided through space by mass we can only map indirectly. The Shapley supercluster is one of our neighborhood's strongest gravitational landmarks. Far beyond our immediate cosmic surroundings lies an enormous concentration of galaxy clusters. Its mass is so great that it helps shape the movement of galaxies across a huge region of nearby space. For astronomers trying to understand why our galaxy is moving the way it is, this structure is a major clue. It is not close in any human sense, but on the scale of the cosmic web, it belongs to our broader environment. Its many clusters form a dense gathering place where gravity becomes deeply influential. When scientists map flows of galaxies, this region stands out like a mountain range on a gravitational map. It reminds us that location in the universe is not only about where things are. It is also about what they are falling toward, what they are leaving behind, and what unseen forces shape their journeys. The local void helps explain the Milky Way's cosmic motion. Our galaxy is not only pulled toward dense regions, it is also affected by the emptier region nearby. A large, underdense space beside our cosmic neighborhood contains far fewer galaxies than average, and that absence matters. Gravity does not push in the ordinary sense, but when one side has less mass and the other side has more, the motion that results can look like being repelled from emptiness. The Milky Way's path is partly shaped by this imbalance. Dense structures attract, while sparse regions offer little to hold galaxies back. This makes the local universe feel like a landscape of slopes, basins, and hollows. We are moving through it because matter is unevenly arranged around us. Even a void can shape our journey, not by grabbing us, but by failing to pull. Galaxies near voids often evolve differently from galaxies in clusters. A galaxy's surroundings can influence its entire life story. Near the edges of voids, galaxies tend to have fewer close encounters with large neighbors. They may keep more of their gas and continue forming young stars for longer periods. In dense clusters, the situation is different. Galaxies can pass through hot gas, feel stronger tidal forces, and experience repeated interactions that alter their shapes. This contrast gives astronomers a natural experiment. Place a galaxy in a crowded region, and its future may become harsher and faster. Place it near a cosmic hollow, and it may evolve at a more measured pace. The stars inside do not know the word environment, but the galaxy as a whole responds to it. The cosmic web becomes a kind of weather system for galactic lives. Spiral galaxies prefer quieter regions of the web. Beautiful disks like the Milky Way need a certain amount of calm to keep their structure. Their thin, rotating forms can be disturbed by frequent collisions, strong gravitational encounters, and crowded cluster conditions. That is why many spirals are found in smaller groups, filaments, and less violent environments rather than at the densest cluster centers. Their arms can continue forming stars when cold gas remains available, and their disks can survive when interactions are not too severe. This does not mean spirals are isolated or fragile in a simple way. They still merge with smaller companions and respond to their surroundings. But compared with the busiest cosmic knots, their preferred neighborhoods often allow more order to persist. When we look at a spiral galaxy, we may be seeing not only a shape, but a record of a relatively gentle cosmic history. Giant elliptical galaxies often grow where filaments and clusters collide. The largest elliptical galaxies are not delicate disks with graceful arms. They are vast, rounded systems, often filled with older stars and shaped by a history of mergers. Many live near the centers of galaxy clusters, where the cosmic web delivers matter from several directions. In these crowded places, galaxies can collide and combine over time. Smaller systems are absorbed. Stellar orbits become scrambled. Gas can be heated or removed, leaving less material for fresh star birth. Eventually, the result may be a huge elliptical galaxy, swollen by many encounters and surrounded by a halo of ancient stars. These galaxies are like archives of cosmic assembly. Their smooth glow can hide a violent past, written in faint shells, streams, and motions that reveal how many smaller galaxies helped build them. Star formation can fade when galaxies fall into crowded clusters. A galaxy entering a massive cluster can lose the very material it needs to make new stars. Clusters are filled with hot gas, and a fast-moving galaxy can feel this gas like a wind. That pressure may strip away its own colder gas, leaving its stellar disk with less fuel for future generations of stars. Gravitational encounters can also disturb its structure, while the cluster environment changes the balance of inflow and loss. Over time, a once blue star-forming galaxy can become redder and quieter. This process does not happen in a single instant, but it can transform a galaxy's destiny. The cluster does not need to destroy the galaxy to change it. It simply changes the conditions around it. A journey into a crowded knot of the web can slowly turn down the lights of creation. Filaments can deliver cold gas that helps galaxies make stars. Stars are born from gas, and galaxies need a continuing supply if they are to keep forming them. In some regions of the cosmic web, long streams of relatively cool gas can flow toward galaxies along large-scale structure. These inflows may help replenish the material used by earlier waves of star formation. The idea is especially important for understanding how galaxies grew in the young universe, when star formation was more intense. Rather than being sealed containers, galaxies can behave like open systems. They take in material from their surroundings, transform some of it into stars, and send some back out through winds and explosions. A filament can therefore be more than a road for galaxies. It can also be a supply line, carrying the raw ingredients from which new suns are made. Some galaxies spin in directions influenced by nearby filaments. A galaxy's rotation can preserve clues about the gravitational forces that shaped its birth. In the cosmic web, matter does not fall inward evenly from every direction. It streams along sheets and filaments, carrying angular momentum into forming galaxies. Studies suggest that smaller galaxies may often have spins aligned in certain ways with nearby filaments, while more massive galaxies can show different patterns after mergers and growth. The details are complex, but the idea is captivating. A galaxy's spin is not just a private property. It may remember the direction from which matter arrived long ago. When we see a disk turning in space, we are watching motion that was built into it by its environment. The cosmic web may leave a subtle signature in the way galaxies rotate, like a current shaping a whirlpool. Galaxy shapes may remember the web environments that formed them. A galaxy can carry its past in its form. Disks, spheres, bars, rings, and distorted systems are not random appearances. They are outcomes of birth conditions, gas supply, mergers, and environmental forces. In sparse regions, a galaxy may preserve a disk for long periods. In dense clusters, repeated encounters and gas loss can push it toward a smoother, older-looking state. Along filaments, steady inflow and occasional group interactions may create a different path again. Astronomers study these shapes to reconstruct histories that cannot be watched directly. A warped disk might hint at a recent companion. A featureless elliptical might point to ancient mergers. A tidal tail may reveal a gravitational encounter still unfolding. The web becomes a sculptor, and every galaxy becomes a shaped object carrying evidence of where it grew. Black holes grow differently depending on their place in the web. At the centers of many galaxies sit supermassive black holes, and their growth depends on how material reaches them. A galaxy in a gas-rich environment may feed its central black hole more readily. A merger can drive gas inward and trigger a dramatic episode of activity. In a cluster, hot gas and environmental stripping may change the available fuel. Along filaments, galaxies may receive fresh material or arrive in groups that increase the chance of encounters. This means black holes are not isolated monsters feeding at random. Their growth is connected to the wider cosmic setting of their host galaxies. When one becomes active, it can shine across enormous distances and influence gas around it. The web shapes galaxies, galaxies feed black holes, and black holes can send energy back into their surroundings. Active galaxies can heat the thin gas around cosmic filaments. When a central black hole feeds rapidly, the galaxy around it can become active and release enormous energy. Some of that energy emerges as radiation. Some can blast outward in jets or winds that reach far beyond the galaxy itself. In regions connected to the cosmic web, this activity may heat surrounding gas and alter how it cools, flows, or falls into other structures. This feedback is one reason galaxy formation is so complicated. Gravity tries to gather matter, but energetic processes can push back. A single active galaxy cannot reshape the entire web, but many such episodes over cosmic time may help explain the temperature and distribution of gas between galaxies. The universe is not only built by attraction, it is also shaped by energy escaping from some of its most extreme engines. The web contains shocks larger than entire galaxy clusters. When matter streams through space and falls into dense regions, it can collide with gas that is already there. These collisions can create shock waves on astonishing scales. Unlike a shock wave from thunder or an explosion on Earth, a cosmic shock may stretch across distances greater than galaxy clusters. It heats thin gas, accelerates particles, and marks places where material is being processed as it joins the web's denser regions. Such shocks are difficult to see directly because the gas involved is so faint. Yet they may reveal themselves through radio emission, X-ray signatures, or effects on passing radiation. They show that the cosmic web is not merely a calm arrangement of galaxies. It has vast fronts of energy and motion, where matter meets resistance and changes state across regions larger than anything in ordinary experience. Magnetic fields may thread through filaments across intergalactic space. Magnetism is familiar around planets and stars, but evidence suggests it may also exist across the far thinner regions between galaxies. Detecting such fields is extremely difficult because they are weak and spread over huge distances. Still, radio observations and studies of polarized light hint that filaments may carry magnetic structure. The origin of these fields is a deep question. They may have been seeded in the early universe, pushed outward by galaxies, or amplified by turbulence and shocks as matter flowed through the web. Even weak fields can matter if they stretch across cosmic distances. They may influence charged particles, radio signals, and the behavior of thin plasma. The idea is remarkable. The universe's largest structure may not be woven only by gravity. It may also be laced with faint magnetism. Cosmic rays may travel through web structures between galaxies. High-energy particles move through space at nearly the speed of light, and their journeys can be shaped by magnetic fields. Some are produced by supernova, active galaxies, or other extreme environments. Once they escape their birthplaces, they may wander through the web rather than traveling in perfectly straight lines. Filaments, shocks, and intergalactic magnetic fields could influence their paths, making the universe into a vast particle maze. By the time a cosmic ray reaches Earth, its original direction may have been altered, which makes its source difficult to identify. This mystery connects the largest structures in space with some of the tiniest visitors to our planet. A particle striking a detector on Earth may have crossed intergalactic regions shaped by filaments and clusters. Its path may carry a hidden story of the web. The hottest web gas can reach millions of degrees. Between galaxies, some ordinary matter exists as an extremely thin, extremely hot plasma. It can be heated when gas falls into large structures, when shocks ripple through the web, or when energetic galaxies send power into their surroundings. Millions of degrees sounds blazing, yet this gas is so diffuse that it would not feel like ordinary heat if you could somehow be there. Temperature measures the motion of particles, and these particles move very fast, but they are spread incredibly far apart. This strange condition makes the gas difficult to detect. It may glow weakly in X-rays or leave subtle marks on background light. Its existence reminds us that the spaces between galaxies are not simple, empty darkness. They can contain matter in extreme states, stretched thin across the universe's largest environments. This gas is hard to see because it barely shines. Astronomy often depends on light, but some of the universe's important material produces very little. Diffuse intergalactic gas may be too thin to glow brightly, even when it is extremely hot. There are not enough particles close together to produce a strong signal. That means astronomers must use indirect methods, stacking data from many regions or studying how the gas affects light from brighter objects behind it. The challenge is a little like trying to see mist spread across an entire continent at night. It is there, but only careful techniques reveal it. This difficulty explains why ordinary matter could remain partly unaccounted for, even in a universe studied by powerful telescopes. The problem was not that the material was exotic. It was that it had become faint, spread out, and almost perfectly hidden. Astronomers search for missing matter using distant quasars as backlights. A quasar can shine so brightly that its light crosses billions of years of space before reaching us. Along the way, that light passes through clouds and filaments of gas. Atoms in the intervening material absorb specific colors, leaving narrow marks in the quasar's spectrum. By reading those marks, astronomers can detect matter that would otherwise be invisible. This technique is one of the most elegant tools in cosmic cartography. The quasar does not need to be connected to the gas being studied. It simply sits beyond it, acting like a lamp behind smoke. Different absorption features reveal different elements, temperatures, and ionization states. Through this method, scientists can find traces of hydrogen, oxygen, and other atoms spread between galaxies, helping to complete the inventory of ordinary matter across the web. Quasar light can reveal invisible gas between galaxies. When a quasar's beam reaches a telescope, it carries a record of everything it crossed. The light may look smooth at first, but when split into a spectrum, it becomes a detailed message. Missing wavelengths show where intervening gas absorbed energy. Each absorption line can tell astronomers something about distance, composition, motion, or temperature. In this way, invisible material leaves visible evidence by removing light rather than creating it. The method is powerful because it can probe gas too faint to image directly. A single quasar sightline is narrow, like a needle through the universe. Many sightlines together create a broader picture of intergalactic matter. The result is almost poetic in its precision. Scientists learn about the darkness between galaxies by studying tiny absences in the light of a faraway cosmic beacon. The Lyman alpha forest traces hidden hydrogen across deep space. Hydrogen is the simplest and most abundant element in the universe, and it leaves a famous mark in quasar spectra. When quasar light passes through many separate hydrogen clouds at different distances, each cloud absorbs light at a slightly different shifted wavelength. The result is a dense pattern of absorption lines known as the Lyman alpha forest. It looks like a thicket of dark marks, but each mark represents real gas somewhere along the line of sight. This forest is one of the best tools for studying the web at great distances, especially in the younger universe. It reveals how hydrogen was distributed long before today's galaxy patterns fully matured. Instead of seeing galaxies alone, astronomers can trace the underlying gas that surrounds and connects them. The forest turns hidden hydrogen into a map of cosmic structure. Some cosmic web gas absorbs X-rays from distant objects. Not all hidden matter reveals itself in visible light. Some of the web's hottest gas is so energetic that it leaves its clearest fingerprints in X-rays. When radiation from a bright background source passes through this thin material, certain atoms can remove tiny portions of the X-ray signal. Oxygen is especially useful because highly ionized oxygen can survive in gas heated to tremendous temperatures. These marks are faint, and finding them requires careful observation, but they can point to matter spread through filaments between galaxies. It is a difficult hunt because the signal is subtle and the material is diffuse. Yet the reward is enormous. X-ray absorption can reveal ordinary matter that has escaped easier detection, not because it is exotic, but because it is hot, thin, and stretched across the great spaces of the web. Fast radio bursts may help weigh matter between galaxies. These brief flashes of radio waves arrive from distant galaxies, sometimes after crossing billions of light-years of space. Along the way, their signals pass through thin clouds of particles between galaxies. Those particles slow different radio frequencies by slightly different amounts, spreading the burst in a measurable way. This delay acts like a cosmic measuring tool. The more particles the burst has crossed, the greater the effect. Because fast radio bursts are bright and sharp, they can help scientists estimate how much ordinary matter lies along their paths. Each burst is like a lightning flash sent through the web, carrying information about the invisible material it encountered. With enough bursts from known distances, astronomers can begin weighing the faint matter between galaxies. A signal lasting only moments can reveal a journey through enormous stretches of space. The web may bend radio signals during their long journey. Radio waves crossing intergalactic space do not always travel through a perfectly empty stage. They may pass through plasma, magnetic fields, galaxy halos, and diffuse gas woven through large-scale structure. These encounters can change the signal in subtle ways. A wave may be delayed, scattered, polarized, or slightly altered depending on the material it crosses. For astronomers, these changes are not just complications. They are messages. A distorted signal can reveal the presence of matter that cannot be photographed directly. It can also hint at magnetism stretching through regions between galaxies. The challenge is separating effects from our own galaxy, from the source, and from the vast web in between. Still, radio astronomy gives the cosmic web another voice. It lets scientists hear the universe's hidden structure through changes in waves that have traveled almost unfathomable distances. Neutrinos may subtly change how the cosmic web grows. Neutrinos are incredibly light particles that stream through the universe in enormous numbers. They rarely interact with matter, which makes them almost ghost-like. Yet they still have mass, and that means they can affect cosmic structure. Because neutrinos move so quickly, they do not clump easily on small scales. Their motion can smooth out some of the fine detail that gravity might otherwise build. The effect is subtle, but the cosmic web is sensitive. Tiny changes in how matter clusters over billions of years can reveal the influence of these elusive particles. This is one of the most surprising connections in cosmology. A particle so difficult to catch in a detector on Earth can leave an imprint across the arrangement of galaxies. The web becomes an enormous instrument for studying the nearly invisible. Measuring the web can help reveal the mass of neutrinos. Laboratories on Earth have struggled to pin down neutrino masses with complete precision because the particles interact so rarely. The universe offers another route. If neutrinos are slightly heavier, they influence the growth of structure in one way. If they are lighter, the pattern changes. By comparing galaxy clustering, gravitational lensing, and the distribution of matter across the web, cosmologists can place limits on how much mass neutrinos carry. This is astonishing because it turns the large-scale universe into a particle experiment. Instead of watching a neutrino strike a detector, scientists watch how galaxies gather over cosmic history. The answer does not come from one galaxy or one filament, but from the combined pattern of countless structures. The smallest known particles leave their weight written across the largest map we can make. Dark matter particles may have left clues in filament shapes. Dark matter cannot yet be identified in a laboratory with certainty, but its behavior can be studied through the structures it builds. Different kinds of dark matter would create different cosmic patterns. Some possibilities allow matter to clump strongly at small scales. Others would smooth out fine structure. Filaments are especially useful because their thickness, branching, and small companion structures can carry information about the properties of the hidden particles. Astronomers compare real surveys with simulations that assume different dark matter candidates. If the observed web matches one version better than another, it narrows the possibilities. This is a remarkable idea. The shape of an immense strand between galaxies may contain evidence about a particle no one has directly seen. The universe has been running the experiment for billions of years. If dark matter is warm, small web structures would blur. Warm dark matter is a hypothetical form that would have moved faster in the early universe than cold dark matter. That extra motion matters. Fast-moving particles resist clumping on smaller scales, which would erase or soften some of the tiny structure that colder particles could preserve. In a warm, dark matter universe, the web might still form on large scales, but its finer details would look smoother. There would be fewer small halos, fewer tiny clumps, and less delicate structure around galaxies. Scientists search for these differences in galaxy surveys, gravitational lensing, and the distribution of distant hydrogen. The question is not only what dark matter is made of, but how fast it once moved. Its ancient speed could still be visible in the sharpness or softness of the cosmic web. cold, dark matter makes a sharper, clumpier cosmic web. In the leading model, dark matter particles moved slowly enough in the early universe for gravity to gather them into small structures. These small clumps then merged into larger ones, building a web with rich detail across many scales. This picture helps explain why galaxies live inside dark matter halos, why clusters form at dense knots, and why simulations produce intricate strands rather than a washed-out pattern. The tumpiness matters because it predicts many small halos, some of which may host faint galaxies, while others may remain dark. Astronomers test this prediction by searching for tiny satellite galaxies, subtle lensing effects, and disturbances in stellar streams. A sharper web is not merely a visual idea. It is a clue about the hidden matter's nature. The universe's texture may reveal the particle beneath it. The web is a natural laboratory for invisible physics. Some of the most important forces shaping the universe cannot be studied by sight alone. Dark matter, dark energy, neutrinos, gravity, intergalactic gas, and magnetic fields all leave marks on the cosmic web. That makes the web more than a structure. It is an experiment spread across billions of light years. No human built it, and no laboratory could contain it. Yet by observing its shape, growth, and hidden matter, scientists can test ideas that reach beyond ordinary experience. A cluster abundance can question dark energy. A filament structure can constrain dark matter. A void shape can test gravity. The web gathers many mysteries into one grand observable pattern. It is nature's own detector, built not from metal or glass, but from galaxies, gas, radiation, and time. Its structure helps test whether gravity works the same everywhere. Einstein's theory has passed extraordinary tests, but the universe offers scales far beyond the solar system. On the largest distances, scientists can ask whether gravity behaves exactly as expected. The cosmic web is central to that question because its growth depends on gravitational attraction over billions of years. If gravity were slightly stronger or weaker on cosmic scales, clusters, filaments, and voids would develop differently. The paths of light through the web would also change. By comparing galaxy motions with gravitational lensing, astronomers can test whether mass pulls matter and bends light in the predicted way. This is a profound use of cosmic maps. The web becomes a ruler for gravity itself. It lets us ask whether the law that guides falling apples also governs the largest architecture in existence. Alternative gravity theories must still explain the cosmic web. Some scientists explore ideas that modify gravity rather than adding unseen matter or unknown energy. These theories can be creative and mathematically elegant, but they face a demanding challenge. They must reproduce the universe we actually observe. That includes galaxy rotation, cluster behavior, gravitational lensing, cosmic expansion, and the large-scale web. It is not enough to solve one puzzle while failing another. The cosmic web is especially unforgiving because it records structure growth across time and scale. A successful alternative must explain why galaxies cluster as they do, why voids have their observed sizes, and why lensing maps reveal so much hidden gravitational influence. This makes the web a testing ground for bold ideas. Any new theory of the cosmos must pass through its filaments, walls, knots, and hollows. The web's growth rate can reveal whether cosmology is incomplete. Cosmologists do not only map where matter is today. They also measure how quickly structure has grown over time. That growth rate depends on the contents of the universe, the expansion history, and the behavior of gravity. If observations show that the web is growing faster or slower than expected, it could point to missing physics. Perhaps dark energy changes with time. Perhaps neutrinos are heavier than assumed. Perhaps gravity needs revision at enormous scales. The signal is subtle, and different measurements must be compared carefully, but the stakes are high. The web is like a cosmic clock, not ticking in seconds, but in the rise of structure from faint beginnings to rich complexity. If that clock runs differently from our model, the universe may be telling us that the story is unfinished. Tensions in cosmic measurements may hide within the web's evolution. Modern cosmology is remarkably successful, yet some measurements do not fit together perfectly. The expansion rate inferred from the early universe differs from some measurements made in the nearer universe. Other observations raise questions about how strongly matter has clumped. The cosmic web may help clarify whether these tensions are signs of hidden errors or hints of new physics. Its evolution connects early conditions with later structure, making it a bridge between different kinds of evidence. By measuring galaxies, lensing, clusters and voids across distance, scientists can watch how the universe moved from smoothness toward complexity. If the timeline refuses to match, something important may be missing. The web is not where every cosmological puzzle began, but it may be where some of them are solved. The web connects the smallest quantum ideas to the largest structures. Few topics in science span such an extraordinary range. The cosmic web reaches across hundreds of millions of light-years, yet its origin may lie in tiny fluctuations from the earliest moments of the universe. Ideas from quantum physics, inflation, particle physics, gravity, and astronomy all meet in its structure. A barely perceptible variation in the young cosmos could become a filament of galaxies. A particle's mass could alter the arrangement of clusters. A change in expansion could reshape the spaces between walls. This is what makes the web feel so profound. It is not just big. It is a record of many layers of reality speaking at once. The smallest effects did not stay small. Given time, expansion, and gravity, they became the largest patterns we can observe. A single galaxy can belong to several web environments over time. A galaxy's place in the cosmic web is not always fixed in one category forever. It may form in a sheet, drift toward a filament, join a group, and eventually fall into a cluster. At each stage, its surroundings change. The available gas, the number of nearby companions, and the strength of gravitational encounters can all shift. This means a galaxy's history may include several environments rather than one simple label. Astronomers try to reconstruct these journeys by studying motions, ages of stars, gas content, and nearby structure. The result is a more dynamic view of cosmic life. A galaxy is not merely born as a spiral or elliptical and left alone. It travels through a changing landscape. Its form today may be the outcome of many neighborhoods passed through across deep time. Galaxies can migrate from sheets into filaments across billions of years. Large-scale structure grows through movement. Matter tends to leave emptier regions, gather into broad sheets, and then drain further into denser filaments. Galaxies can take part in this slow migration. A galaxy that once lived in a relatively spread-out sheet may gradually move toward a filament as gravity reshapes the surrounding landscape. The timescales are immense, but the process is central to the web's evolution. It is not a simple inward fall toward one center. It is a layered flow, guided by the uneven distribution of mass around each region. This movement can alter a galaxy's future by changing its access to gas and companions. The web, therefore, has pathways of development. Over billions of years, galaxies do not only evolve internally, they relocate within the architecture that surrounds them. Cosmic voids expand as matter drains into surrounding walls. A void begins as a region with slightly less matter than average. Because it has less gravity pulling inward, nearby denser regions can gather material more effectively. Over time, matter flows away from the underdense center toward surrounding sheets and filaments. The void becomes larger in a relative sense, while its boundaries grow more defined. This expansion is not an explosion from the middle. It is the outcome of imbalance. Gravity pulls matter toward where matter already is, leaving emptier places emptier still. Voids can eventually occupy most of the volume of the universe, even though most of the mass lies in the web around them. They are not failures of structure. They are structure turned inside out. Their growth helps give the cosmic web its dramatic contrast between crowded edges and vast interiors. Void galaxies can be isolated laboratories for slow evolution. Galaxies inside voids often live with fewer close neighbors and fewer disruptive encounters. That makes them valuable for understanding how galaxies change when cosmic interference is reduced. Some may remain gas-rich and continue forming stars at a modest pace. Others may be small, faint systems that would be harder to notice in busier regions. Because they are less affected by cluster conditions, they can help scientists separate internal processes from environmental ones. A void galaxy is not untouched by the universe, but it may have had a calmer history than a galaxy in a dense knot. This makes it a kind of natural control case. By comparing void galaxies with those in filaments and clusters, astronomers can learn how much of galaxy evolution comes from nature and how much comes from neighborhood. Some voids may preserve conditions from a quieter cosmic past. Because voids are underdense, structure formation inside them proceeds more slowly than in crowded regions. This means some void environments may resemble earlier stages of cosmic development in certain ways. Their galaxies can be less massive, less chemically enriched, or less transformed by repeated interactions. The gas and dark matter there may have followed a more gradual path through time. That makes voids useful for studying processes that denser regions have already complicated or erased. They are not time machines in a literal sense, but they can preserve simpler conditions for longer. Scientists look to them for clues about low-density growth, faint galaxies, and the influence of environment. In the great story of the web, voids are the pauses between louder passages. They hold a slower rhythm, and that slower rhythm can reveal hidden details. The web's emptiest regions still contain dark matter. Even the most barren cosmic voids are not completely free of mass. They contain dark matter at lower density than the web's crowded regions, along with sparse gas and occasional faint galaxies. This matters because voids are not holes in the universe. They are underdense regions within the same cosmic fabric. Their dark matter distribution affects how they expand, how their boundaries form, and how small galaxies inside them move. Studying voids can therefore test the nature of dark matter in a different way from studying clusters. Clusters show where gravity has gathered matter most intensely. Voids show what happens where matter is scarce. Both are needed for the full picture. The emptiest places in the universe still belong to the hidden framework, and even their darkness has weight. Nothing in the cosmic web is perfectly still. The largest pattern in the universe may look frozen when we see it on a map, but every part of it is in motion. Galaxies orbit inside groups. Groups fall toward clusters. Gas streams along filaments. Voids change as matter drains toward their edges. Even the clusters themselves move through the wider gravitational landscape. These motions are slow only by human standards. Across cosmic time, they become powerful enough to reshape entire regions. A galaxy that appears fixed in a survey is really traveling through an invisible current of gravity, expansion, and local attraction. This is one of the great surprises of large-scale astronomy. The universe is not a still arrangement of distant lights. It is a moving structure, and every galaxy is part of that motion. Even the web itself has a kind of drift. The entire structure flows, stretches, and rearranges across cosmic time. The cosmic web is not a finished sculpture. It is more like a vast process unfolding across billions of years. Dense regions gather more mass, while sparse regions become increasingly open. Filaments feed clusters, clusters merge, and galaxy groups are drawn into larger systems. At the same time, the expansion of space stretches the greatest separations, changing which structures can remain connected. If we could watch the universe in fast motion, the web would not sit calmly in place. It would thicken in some regions, widen in others, and shift as gravity and expansion compete. The pattern would remain recognizable, but never identical from one era to the next. This makes every cosmic map a portrait of a moment. The web has a past, a present, and a future still being written. Light crossing the web can take hundreds of millions of years. A filament or void can be so enormous that light itself needs an almost unimaginable span of time to cross it. This gives cosmic structure a strange depth. When we look across one of these regions, we are not seeing every part at the same moment. The nearer side may be shown from one age of the universe, while the far side appears from an earlier age. Even a single structure can contain time inside its image. This is difficult to feel because light seems instant in ordinary life. In the cosmic web, light becomes a slow messenger. It carries information across distances that can outlast species, continents, and entire chapters of planetary history. To map the web is therefore to map space and time together. Distance becomes memory, and every view arrives late. We see the web as it was, not as it is. Astronomy is always a study of delayed arrivals. The farther a galaxy is, the older its light must be by the time it reaches us. This means cosmic maps are not snapshots of the universe at one universal present. They are layered records of different ages. A nearby cluster may appear almost as it is now, while a distant filament shows how matter was arranged billions of years ago. This is not a flaw. It is one of astronomy's greatest gifts. It lets us study the web's evolution without waiting for time to pass. Looking farther away is looking farther back. The universe becomes its own archive. In every deep survey, scientists are not only asking where matter is, they are asking when this light began its journey and what the web looked like then. Distant filaments show younger chapters of the universe's story. When astronomers map structures far away, they are seeing the cosmic web at earlier stages of growth. Those filaments may be less mature than nearby ones, because their light began traveling when the universe was younger. Their galaxies may still be forming stars rapidly, building mass and interacting with gas in ways that later changed. This makes distant structure especially valuable. It shows how the web looked before billions of years of mergers, heating, and expansion added complexity. A faraway filament is not simply another region in space. It is a preserved chapter from an earlier era. By comparing distant filaments with nearby ones, scientists can reconstruct how the web matured. The method is almost like studying forests of different ages at once, except the forest is made of galaxies and time. Nearby filaments reveal what the web became after long growth. The structures closest to us show the cosmic web after billions of years of gravitational development. Their galaxies have had more time to merge, exhaust gas, build heavy elements, and respond to their environments. Clusters at their intersections may be massive and settled, though still evolving. Voids around them may be large and clearly defined. These nearby regions are easier to study in detail, so they reveal processes that distant surveys can only hint at. Astronomers can measure galaxy shapes, motions, gas content, and surroundings with greater precision. This makes the local web a kind of mature specimen. It tells us what early seeds can become after time has done its work. Nearby does not mean ordinary. It means richly readable, full of clues written across galaxies that have lived through most of cosmic history. The web lets astronomers study cosmic history in 3 dimensions. A normal picture of the sky gives direction, but not depth. The cosmic web becomes truly meaningful when distances are added. With distance, astronomers can place galaxies into a 3-dimensional structure and separate nearby neighbors from faraway lookalikes. They can see whether galaxies belong to clusters, filaments, sheets, or voids. They can also compare regions from different cosmic ages, because distance carries a time delay. This turns the sky into a layered history. Instead of a flat sprinkling of lights, it becomes a vast map with depth, motion, and age. The web is one of the reasons modern astronomy feels so powerful. It does not merely show beautiful objects. It reveals the universe as a connected structure where every galaxy has a position in space, a place in time, and a relationship to everything around it. Redshift surveys turn galaxy distances into maps of deep time. As the universe expands, light from distant galaxies is stretched toward redder wavelengths. Astronomers use this redshift to estimate how far away galaxies are and how long their light has been traveling. When millions of redshifts are gathered, something extraordinary happens. The galaxies become points in a 3-dimensional map, and the cosmic web appears. Redshift surveys have revealed walls, filaments, clusters, and voids that would remain hidden in ordinary images. They also allow scientists to measure how structure changes with distance, which means how it changes with time. A redshift is therefore more than a number. It is a clue to location and history. Each measurement places one more galaxy into the grand architecture. Enough measurements together become a map of the universe, learning how to take shape. Some filaments are found before their galaxies are fully mature. In the distant universe, astronomers can find large-scale structures where young galaxies are still actively forming and growing. These early filaments do not always resemble the settled patterns nearby. Their galaxies may be smaller, more irregular, richer in gas, and brighter with new stars. The surrounding material may still be falling into place. Finding such structures is thrilling because it shows the web during construction. We are not only seeing the finished network, we are catching it while its galaxies are still becoming what they will be. This helps answer a deep question. Did galaxies form first and then arrange themselves, or did the larger structure guide their formation from the beginning? The evidence points toward a close relationship. Young galaxies and young filaments grow together, shaped by the same gravitational blueprint. The first galaxies likely formed inside the web's earliest knots. In the young universe, matter was not evenly ready to make galaxies everywhere. The densest early regions had the strongest gravitational pull, so gas collected there first. These knots became natural birthplaces for the earliest galaxies. Inside them, gas could cool, collapse, and ignite stars more easily than in emptier surroundings. Those first systems were probably smaller and more chaotic than modern galaxies, but they began the long process of cosmic enrichment. Their stars forged heavier elements, their explosions pushed material outward, and their light helped transform the universe around them. The earliest knots were therefore more than dense places. They were the first construction sites of visible structure. The web did not wait for galaxies to appear randomly. Its densest beginnings helped decide where the first lights would gather. Cosmic reionization spread through a young web of matter. After the first stars and galaxies ignited, their ultraviolet light began changing the gas between galaxies. Much of the universe's hydrogen had become neutral after the early hot phase faded. As new sources of light appeared, bubbles of ionized gas grew around them. Over time, these bubbles expanded and overlapped, transforming intergalactic hydrogen across huge regions. This process did not happen evenly everywhere at once. It followed the pattern of early structure, beginning around the places where galaxies formed most intensely. Dense knots and filaments helped shape where ionizing light emerged, while surrounding gas determined how it traveled. Reionization was one of the universe's great phase changes. It turned the young Webb from a mostly neutral environment into a more transparent cosmic landscape, preparing the stage for the galaxies we observe later. Ancient hydrogen clouds once outlined the universe before galaxies dominated. Before galaxies became the main traces of structure, hydrogen gas filled the cosmic landscape in delicate patterns. This gas followed the gravitational influence of dark matter, gathering more strongly in some regions and thinning in others. It did not shine like stars, but it could absorb light from background sources and leave spectral fingerprints. In the early universe, these hydrogen clouds revealed a web that was still raw and gas-rich. They traced the underlying structure before galaxies fully took over as the visible markers. This is a powerful reminder that the web is not only made of galaxies. Galaxies are bright highlights in a much broader arrangement of matter. Long before the night sky was filled with mature systems, hydrogen was already sketching the universe's shape in faint, readable lines. The web may have guided where the first stars ignited. The first stars needed dense pockets of gas, and those pockets were not scattered equally. They were most likely to form inside small dark matter halos along the early web's densest regions. There, gravity gathered hydrogen and helium until cooling and collapse could begin. These first stars may have been massive, brilliant, and short-lived. Their light pierced the darkness, and their explosion seeded nearby gas with the first heavy elements. The locations of those stars mattered because they influenced where later galaxies formed and how surrounding gas changed. In this way, the web may have guided the universe's first flames. It provided the gravitational pathways and knots where raw matter could become light. The first stars were not just isolated sparks. They were born within a structure already taking shape. Future telescopes may map the web before galaxies were common. One of the great ambitions of astronomy is to see structure from the era before mature galaxies filled the universe. Instead of relying only on starlight, future instruments may trace hydrogen gas itself. This would reveal the cosmic web at an earlier and more delicate stage, when matter was still settling into the patterns that later produced galaxies and clusters. Such maps would be revolutionary. They could show how the first luminous objects emerged, how reionization spread, and how ordinary matter followed dark matter into structure. The challenge is enormous because the signals are faint, stretched by expansion, and tangled with foreground noise. Yet the promise is extraordinary. Scientists may one day map not just the web of galaxies, but the web before galaxies, when the universe was still preparing its first great lights. The square-kilometer array could trace hydrogen through cosmic filaments. This next-generation radio observatory is designed to be extraordinarily sensitive. One of its great goals is to study hydrogen across cosmic time by detecting radio signals from the 21-centimeter line. That signal comes from neutral hydrogen, which can reveal where gas lies even when stars are absent or scarce. For the cosmic web, this could open a new kind of map. Instead of seeing only galaxies, astronomers could trace the gas that feeds them and surrounds them. The instrument's reach may help scientists study how hydrogen collected into filaments, how it changed during reionization, and how it later supplied galaxy formation. It is a vision of astronomy where the dark spaces between galaxies become measurable. The web's faintest material may become visible through radio whispers from hydrogen itself. The cosmic web may eventually fade from view in deep future time. The universe's largest structures are not guaranteed to remain visible forever. As expansion continues, distant galaxies and filaments will move farther away, and their light will become increasingly stretched and faint. In the very far future, observers in a galaxy like ours may see a much smaller, accessible cosmos. The grand web we map today could disappear beyond observational reach, not because it vanishes locally, but because its distant parts become hidden by cosmic expansion. This gives our era a special importance. We live at a time when ancient light still reaches us from across the universe, and large-scale structure can still be studied in breathtaking detail. Future skies may not offer the same view. The cosmic web is not only a structure in space, it is also a temporary gift of cosmic timing. Dark energy could leave distant filaments forever unreachable. As accelerated expansion continues, some regions of the universe may recede so quickly that light sent from us will never reach them. This does not affect nearby bound systems, but across the largest distances it changes what can ever be contacted or observed. Distant filaments that are visible now may eventually slip beyond the horizon. Their light can still arrive for a time, but any new signal from them may become impossible to receive in the far future. This creates a profound boundary. The web may be enormous, but not all of it is permanently accessible. Dark energy turns cosmic geography into cosmic separation. It means the universe contains places that are real, structured, and full of galaxies, yet destined to become unreachable. The grand network may slowly lose its farthest connections. Future civilizations may see only their local cosmic island. Imagine astronomers living unimaginably far in the future. If they arise in a galaxy bound to a local group of galaxies, they may see that group clearly. Beyond it, however, accelerated expansion may have carried distant structures out of sight. The cosmic microwave background may be too stretched to detect, and faraway galaxies may have faded beyond practical observation. Such observers might believe their local island is all that exists. They may have no easy evidence for the cosmic web, the Big Bang, or the vast galaxy-filled universe we can map today. This thought is humbling. Knowledge depends not only on intelligence, but on when in cosmic history observers exist. We live in a rare window, when the universe is old enough to show structure, but young enough that its distant pattern remains visible. The web reminds us that emptiness can have structure. The great spaces between galaxies are easy to imagine as nothing. Yet the cosmic web teaches a richer lesson. Voids, gaps, and thin regions are not meaningless absences. They help define the structure around them. Their boundaries guide where galaxies gather. Their growth reveals how gravity has moved matter across time. Their sparse contents test models of dark matter and cosmic expansion. In the universe, emptiness is not just a blank. It has shape, history, and influence. This idea reaches beyond astronomy in a beautiful way. The pattern exists because there are both crowded places and open ones. Without the voids, the filaments would not stand out. Without the silences, the music would lose its form. The web shows that even what seems missing can be part of the design. Every galaxy is part of a pattern larger than itself. No galaxy exists in complete isolation from the universe around it. Each one has a place in the greater arrangement of matter, whether in a cluster, a filament, a sheet, or near the edge of a void. That place can influence how it forms stars, gathers gas, meets neighbors, and travels through cosmic time. The Milky Way is no exception. Our home galaxy belongs to a local group, a larger flow, and a vast network that stretches far beyond sight. This final perspective is both scientific and deeply moving. The stars above us are not scattered sparks without context. They belong to a galaxy, and that galaxy belongs to a web. The universe is connected on scales larger than imagination, and every point of light is part of a pattern still unfolding. And so we have drifted across the largest known pattern in the universe. We have followed galaxies into filaments, wandered through immense voids, and traced the hidden pull of dark matter as it gathers the cosmos into shape. We have seen how ancient ripples became galaxy clusters, how invisible gas lingers between the stars, and how even emptiness can have structure, movement, and meaning. The cosmic web reminds us that nothing is truly separate. Every galaxy belongs to something larger. Every cluster sits within a greater design. Even our own Milky Way is carried within this vast arrangement, one small home in a universe woven with gravity, time, and light. And now, as that thought settles, let your mind begin to soften. There is nothing more you need to hold on to tonight. Let the great filaments fade into the dark. Let the distant galaxies become small points of light. Let the wide spaces between them open gently, with room enough for every thought to slow down. If you enjoyed this journey, you are welcome to like, subscribe, or leave a thought below. It helps others find their way here too, one sleepy soul at a time. And if you happen to still be awake, another gentle video is waiting on the screen. But for now, let your shoulders loosen. Let your breathing find its own easy rhythm. Let the day fall away, strand by strand, until only stillness remains. Sleep well, and good night.